Even though the place where we worry about mercury pollution is usually in the water, most mercury is actually emitted into the atmosphere, and it will go around the globe, undergo chemical reactions. What happens in the atmosphere with transport and chemistry really determines where mercury ends up and has a toxic impact, you could say, and rather than where the pollution source is, because it will get into the air and can travel long distances.
Hello and welcome to the Pittcon podcast. In this episode, we sit down with Seth Lyman to discuss recent advances in the measurement of atmospheric mercury. Thank you so much for joining us here today, Seth. Could you first briefly introduce yourself, your role at Utah State University, and your primary research focus?
Yeah, so I am the director of Utah State University's Bingham Research Center. I am also a research professor in the chemistry department at USU. My research focus is really pollution in the atmosphere, and I study a lot of aspects of that, from pollution emissions, chemistry, instrument development, atmospheric fate, all those sorts of things. A lot of what I do is atmospheric mercury. So mercury, everybody's familiar with mercury as the silvery liquid. Like other liquids, it has a vapor phase and gets into the air and then can react chemically before it gets involved in polluting the environment. And so that's a particular focus of mine.
Mm-hmm. And why is it important to focus on atmospheric mercury? Why should we be so interested in or concerned about it?
Yeah, well, most mercury pollution, or rather, when mercury has a toxic impact, it's usually in aquatic systems. So you are probably aware of mercury consumption advisories in fish, for example. But so even though the place where we worry about mercury pollution is usually in the water, most mercury is actually emitted into the atmosphere, and it will go around the globe, undergo chemical reactions. What happens in the atmosphere with transport and chemistry really determines where mercury ends up and has a toxic impact, you could say, and rather than where the pollution source is, because it will get into the air and can travel long distances. So understanding how much is in the air, what kind of mercury, its chemical nature in the air, and where chemical reactions and deposition occur, helps us understand where mercury that might be, say, in the San Diego Bay came from before it got here.
That's fascinating. And are there any challenges in analysing or characterising these atmospheric mercury compounds?
Yes, a lot of challenges. So the biggest one is that mercury exists in the atmosphere, but the concentrations are really low. So we measure it in parts per quadrillion. So for each molecule of mercury, then there's a quadrillion molecules of everything else. And our research group focuses in particular on oxidized mercury compounds. They exist in the range of about 0 to 10 parts per quadrillion. So that's 0 to 10 molecules of oxidized mercury per quadrillion molecules of everything else. And the other challenge, well, there are two other challenges. One is that oxidized mercury compounds are only a little bit volatile. So they may exist in the gas phase in the atmosphere, but as soon as they come into contact with the surface, they want to stick to it. Any surface, really, even like Teflon or something very inert. So that's a challenge, keeping them in the gas phase long enough to analyze them. The other challenge is that they tend to be chemically labile. They'll break apart back to elemental mercury and other stuff very easily. So we have to find surfaces and ways of handling them that are extremely inert and also warm to keep them in the gas phase.
Mm-hmm. And how would you contextualize the amount of atmospheric mercury compared to, say, some other compounds we may be more familiar with, such as CO2 or other volatile compounds?
Yeah, as far as the amount in the atmosphere, well, CO2 exists in these days more than 400 parts per million. Ozone is another common pollutant. It's in the range of around, in the background, 20 to 50 parts per billion. There's some other organics, like maybe benzene in the background atmosphere, are in the low parts per trillion range, or maybe mid parts per trillion range, depending on where you're at. So we're about an order of magnitude lower than these ultra trace background chemicals.
And could you discuss the different methods and technologies that you are developing or you're involved with that are being used to identify and quantify these such low levels of atmospheric mercury compounds?
Yeah, well, it turns out several really good commercial analyzers for elemental mercury in the atmosphere that can measure those low parts per quadrillion levels well. Elemental mercury is fairly inert and more volatile than oxidized mercury. There's one company, well, I guess you could count it as two. There have been attempts to make a commercial instrument for oxidized mercury compounds in the air. The one that took off or kind of got some traction, it turns out to be biased low. And now there's over a dozen papers showing that this method of measuring oxidized mercury is strongly biased low, and the extent of the bias depends on where you're at and the chemistry of the atmosphere. And so there's been an effort, or rather really our effort has been to develop alternative methods. And we've worked with a lot of partners to do that. One instrument that we've put together measures oxidized mercury indirectly. You measure total mercury, you measure elemental mercury, and then take the difference. And that's challenging because there's a lot more of total mercury and elemental mercury than there is oxidized mercury. So we have to make very precise measurements. We've been able to do that and demonstrate that in a couple of cases. Another aspect of our work is making sure the measurements are correct, so building calibration systems. The reason this commercial instrument got into the market and got a lot of traction before it was found out that it didn't work well is there was no method to calibrate those measurements. And that's something we've been working on for really about 10 years, is methods to calibrate oxidized mercury. And we use permeation tube-based methods that are NIST traceable and can deliver these very low concentrations of oxidized mercury in ambient air while these systems are sampling ambient air, because we found that mercury measurement systems can behave differently in ambient air versus like an inert gas or a scrubbed air.
That's really interesting. And building on your efforts in advancing the calibration and as well as your partnerships with industry, could you kind of walk me through how working in research, how you approach this? Like, how do you reach out to different companies that are manufacturing these products and technologies? And how do you say, look, there might be a problem here, but we can help?
Yeah, that's a good question. I think one way that we do that is by looking at analogs in other fields of chemistry or other fields of analysis. So, for example, semi-volatile organics can give us kind of ideas about how to deal with semi-volatile metal-containing compounds, I guess, right? So when we're looking at like analytical companies or manufacturers, then we kind of talk from that angle because there really isn't another metal that behaves like mercury in the atmosphere, certainly not one that has kind of the toxic impact and the imperative need to measure it as mercury, right? And so we kind of have to talk in terms of analogies. And then also just trying things out, experimenting. We think this might be a method that works. Let's buy some parts, build something, and see if it works, right? And several companies have been really great at helping us as we kind of put things together. As far as companies that currently make mercury instrumentation, one challenge is that even though understanding mercury in the atmosphere is important, it's not like, say, ozone or CO2, where there are kind of regulatory pushes that cause a government or an agency or whatever to need a lot of these instruments. And so commercially, it can be a challenge to convince a company to kind of build the commercial instrument, especially since the last time that kind of happened, then it ended in really failure, right? The instrument was shown later to not work. So we're not really at the stage of taking these instruments and putting them into a commercial operation yet, I don't think.
Mm-hmm. Hopefully in the future.
I think so, yeah, I hope so.
So looking more specifically to your research, could you tell me a little bit about how material selection and temperature control can impact the accuracy of mercury measurements?
Yeah, and those are related in the instruments that we build. So we need to have elevated temperatures so these oxidized mercury compounds will stay in the gas phase. We find that if they stick to a surface, they tend to never come off of that surface as oxidized mercury compounds. They'll reduce back to elemental mercury, and then that elemental mercury will come off, and then we've lost our sample. So we use fairly high temperatures, around 150 C, for most of our calibration and analytical instruments. And then at that temperature, then some inert materials start to perform a little less well, like Teflon tends to become more porous and at higher temperatures. And so we've experimented with stainless steel, coatings on stainless steel, including sulfonert and other deactivated fused silica coatings, and those seem to do well. At higher temperatures, they are as inert as Teflon for these oxidized mercury compounds and less porous, and so we can kind of crank up the temperature as we need to and still have that inert property to them.
Oh, that's really interesting. So you've spoken a little bit about the challenges of different technologies that are being used in this field of research and how hopefully in the future we can overcome that. Building on this, what do you see as the next big breakthrough or the next big development or even a challenge in the field of atmospheric mercury research? And how do you envision your work contributing to this?
Yeah, that I think is a good question. I think there are a lot of challenges remaining. Perhaps the one that the kind of atmospheric mercury community talks about the most is the instruments that we've developed to measure oxidized mercury in the atmosphere aren't compound specific. They measure total oxidized mercury. And in fact, we don't know with certainty what the oxidized mercury compounds in the atmosphere are because there are no methods to measure them. The concentrations are too low, so you can't do direct measurements with mass spectrometry or something like that, at least not currently. And so all the methods are kind of indirect. You collect a sample and then you desorb it as elemental mercury or something like that. So that's probably the biggest challenge. We've made attempts at that. So using our our mercury handling know-how to try to get oxidized mercury, so we do a pre-concentration and then thermally desorb into a mass spectrometry system. The problem is that thermal desorption step tends to break the oxidized mercury compounds down. We work with a group at the University of Nevada has done a lot of work and is continuing a lot of work to look at different surfaces that might be kind of more gentle in their ability to release oxidized mercury compounds into a mass spectrometer or a similar instrument. And so as far as how our work might contribute to that, even though so far we've failed, right? We don't have the right surface to collect oxidized mercury, then release it intact. At least we're in a place where we have more and more confidence about how to transmit oxidized mercury onto that surface and then from that surface into an analyzer where it could be chemically identified. So we're partway there, I think, yeah.
It sounds quite exciting. It sounds like you're constantly learning new things and new approaches, and also like you'd mentioned earlier about how it's a really close-knit community as well in this field. It must be quite nice being able to collaborate and speak to others and learn different things as well.
Yeah. There is especially when you look at oxidized mercury in the atmosphere and developing methods, there's probably about 5 research groups in the world. So our group, one in Nevada, there's a group in Slovenia, a group in China, and maybe a couple others that kind of pile on sometimes. And so it is a small group that really tries to work together and advance the science together. Yeah.
Pittcon Perspectives. Unforgettable Pittcon moments from the experts.
You mentioned that it's your first time attending Pittcon and your first time being invited as a speaker. How did it feel to be invited, and what are your first impressions of Pittcon this year?
I was extremely flattered to be invited. I feel like in some ways the work that we do is a little bit niche, I guess, but I hope that what I have to say in my presentation will kind of spark broader interests and ideas for others, and maybe new collaborations. And as far as my first impressions, I've only been here today so far, but I've already gotten some kind of exciting ideas about where to go next. A lot of, I guess I think my scientific interest is more in environmental processes, but my approach has been in developing instrumentation to help us understand those processes. So very instrument heavy and method and analytically heavy. And so most of the conferences that I attend are more on the processes. And it's kind of exciting to be talking to people who are focusing on the analysis more, because if we don't do the analysis right, we can't understand the processes in the environment.
It's like you found your people.
Yeah, yes.
And looking ahead to the week, you've spoken a little bit already about what you've really enjoyed in your first impressions. What are you most looking forward to about Pittcon 2024 in San Diego for the rest of the week, and even potentially next year as well?
Well, I am signed up for a workshop on measurement uncertainty. And when you're building your own new instruments, then knowing how confident you can be in that instrumentation is really important. So I'm excited for that. I also am looking forward to meeting more parts manufacturers, instrument developers that we work with. Usually it's emails and every once in a while a phone call. It'll be nice to see people face to face.